Okay, so in this video, we want to consider the topic of orthogonal projections, and if you remember, orthogonal means perpendicular. This will be a simple application of the dot product, but as we will see in our next videos, when we consider problems of distances, this will come in really handy. So here's the setup. Suppose we have a non-zero vector v. Suppose it looks like this. And suppose we have a second vector u. And let's say we position the initial point of u onto the initial point of v. The idea of an orthogonal projection is to decompose the vector u into a sum of two vectors, one vector being parallel to v and the other vector being perpendicular to v. So imagine that you were shining a light onto vector u, so then you would have the shadow of vector u onto vector v, but you would shine a light in such a way that the shadow on vector v, the tip of the shadow, would form a segment with the endpoint of u that is perpendicular to vector v. And now, so imagine that you are collapsing vector u, onto vector v in a perpendicular fashion. So we can now decompose our vector u as this vector. Let's call it w1, plus this vector. Let's call this vector w2. And now let me just make this a little darker. And we give w1 a very special name. w1 is called the orthogonal projection of u onto vector v. So really just think of collapsing vector u onto vector v, but in a perpendicular fashion. So we usually write w1 equals, and again, w1 is said to be the orthogonal projection of u onto v, so we write proj for projection, and v is not moving, v is staying there, and we are collapsing vector u onto vector v, so we are projecting vector u onto vector v. And that's the notation. So this reads the projection of u onto vector v. And now a natural question to ask is, how do we find w1, the projection of u onto v, and w2, which is the so-called orthogonal component, right? Because it is a component of u, because u is w1 plus w2, but w2 is orthogonal to vector v. So w2, if you want, is called the orthogonal component. Okay, and now again, imagine that you have vector u, you have vector v, and from these two vectors alone, how can we find w1, the projection of u onto v, and w2, the orthogonal component? Well, let us write down what we know so far. What do we know? First thing, u is the sum of w1 and w2. And because we know u to begin with, if we can find a way to obtain w1, then we'll know u and we'll know w1, and naturally w2 is simply u minus w1. So all we have to do is find w1. Well, what do we know about w1? Well, it is lying on vector v, therefore w1 is parallel to v. But two vectors are parallel if and only if one is a multiple of the other. So we know that w1 has to be some multiple of v, say k times v, for some real number k. And finally, the vector w2 must be perpendicular to v, or orthogonal. And if you remember, two vectors are perpendicular if and only if they have a dot product of 0. So w2 dotted with v must be 0. And now with these three equalities, we should be able to solve for w1. Well, look at this equality. Let us isolate w2 as u minus w1. And now let us replace w1. So we've used this equality, gone. Let us now replace w1 in terms of v, kv, just some multiple of v. So we get u minus kv. And now let us plug this in the third equality. The vector w2 dotted with v must be equal to 0. Let us replace in here w2 by u minus kv. Let's see what we get from this. w2, which is u minus kv, dotted with v must be 0. And if you look at this equality, we know everything but k, because we are starting with vectors u and v being known. So we know vector u, we know vector v. The only unknown here is k. We can easily solve for it. If you remember, the dot product behaves like regular scalar multiplication, so we can distribute here. We'll have u dot v minus k v dot v. So minus k times v dotted with v. This is equal to 0. We'll send this onto the right-hand side. Therefore, u dot v equals k times v dot v. And finally, since the vector v was assumed to be a non-zero vector, it has a positive length, and v dot v is the length of v squared, so this is a positive quantity, so we can then solve for k by dividing across by v dot v. And so k is quite simply going to be u dot v divided by v dot v. And if you think about it, we're done, right? The vector w1 which is what we call the projection of vector u onto vector v, right? We project vector u against vector v, and we get w1, the so-called projection. So w1 is the projection of vector u onto vector v. And now if you remember, w1 was just a multiple of v, but we now know what the multiple is. It's u dot v over v dot v. Voila! So k, which is our scalar multiple given by u dot v over v dot v, times the vector v. So there you have it. You have the projection of u onto vector v, and that is again the component of u parallel to v. And now we want the complement, the orthogonal component, and that's just w2. And that's quite simply, well, u minus the projection. So you can find your projection first with this formula. This will give you the vector component of u along v, the projection. And the orthogonal component is, as we have said before, simply vector u minus the component of u along v, the projection. So this is simply u minus the projection of u onto vector v. So there you have it. And if we summarize here, you can compute this vector using this formula. Once you have it, u minus w1 gives you w2, and we know that u will be the sum of the projection of u onto v plus the orthogonal component. And again, the vector w1 is parallel to v, so it is called the component also, the component of u along v because it is parallel. w2 is the component of u that is, recall, perpendicular to vector v. So w1 is parallel to v, that is the projection. w2 is perpendicular to vector v. And this is the so-called decomposition of u into a sum of two vectors. This is the first component vector, this is the second component vector. This vector is parallel to v, this vector is perpendicular to v. The vector component of u parallel to v is called the projection of u onto v, and it's given by u dot v over v dot v times the vector v. And that's the projection. Now, there's one last thing that we'll prove about this projection, this operation. But if you think of it, the reason why this is useful to break up a vector as a vector parallel to a given vector and one that is perpendicular to the given vector, this will be really useful in problems of distances. Because if you think of it geometrically, if you have two objects in space and you want to find the distance between the two objects, think of how you would draw the distance. You would connect the two objects with a line segment, and the line segment would have to meet the two objects in a perpendicular fashion. So this will come in really handy in problems of distances. One last property of the projection, and that is, would the projection of u change on to vector v if v was longer, shorter, or in the opposite direction? And the answer actually is no. The length of v doesn't matter, only the direction of the vector. And even the opposite direction would do the same. So the way to think about this is when you project vector u onto vector v to obtain this vector, you really are projecting on the direction spanned by vector v. Let's see what that means, and then we'll prove it, and the proof will be very easy. So what do I mean by when I project u onto vector v, I am really projecting u onto the direction spanned by vector v. So imagine that we have the following three pictures. I draw vector v like this, and I draw vector u as we did before, like this. If you project vector u onto vector v, so you project, think of again squashing vector u against vector v, but of course you squash vector u in a perpendicular fashion. So you connect the endpoint of u onto vector v in a perpendicular fashion, and the vector you get is the projection of u onto v. Now what if the vector, let's try and draw the same picture, what if the vector v was much shorter but still in the same direction? So let me try and reproduce the picture, keeping u as close to the original picture as possible. This is vector u. And let's draw vector v almost parallel, but shorter now. Would the projection of u onto vector v be any different, as long as v has the same direction as the previous vector v? And the answer is no. Imagine the line spanned that is generated by vector v. And if you project vector u onto vector v in a perpendicular fashion, once again, geometrically you simply connect the endpoint of vector u onto the line spanned by vector v, and of course you will connect with the line in a perpendicular fashion. And the projection is again the exact same vector. This is still the projection of u onto v, and both vectors are exactly the same. So whether v is much longer than u or much shorter, when you project u onto v, as long as the direction is the same, the projection will be the same vector. And the direction of v can also be opposite. So let's try and reproduce our vector u. And what if vector v was parallel to the previous two vectors, but had the opposite direction? And what if once again we wanted to find the projection of u onto vector v? Would it be different than the previous two vectors? And the answer once again is no. Consider the line spanned by vector v. Once again we are projecting u against this line, against the line spanned by vector v. Therefore we connect the endpoint of u onto the line in a perpendicular fashion. And so once again the vector here is the same as before. This is still the projection of u onto v. So the length of the vector v does not matter, and as long as the vector has the same direction or opposite direction, so as long as of course the vector, simply put, is parallel to v, the projection of u onto that vector will be the same. Let's prove this. And how do we state this? We're saying if you project vector u onto any vector parallel to v, you should get the same result. So let's write this down, and then let's prove it. If we project vector u onto any vector that is parallel to v, well, vectors are parallel if one is a multiple of the other. So all vectors that are parallel to v, whether they have the same or opposite direction, must be simply multiples of v. So k v. And we're saying that this would still be the same as projecting u onto the original vector v. And so it doesn't matter whether you have a longer, a shorter vector, or even with opposite direction, the projection will be the same. Of course, k can't be 0 because otherwise you kill the vector, and then you get no direction for your projection, and then it doesn't make sense. So this is true for any non-zero real number k. And the proof is just one line. We will simply use the formula for the projection. So recall the formula for the projection of u onto v. So if you project vector u onto vector v to obtain this component, we know this is simply going to be u dotted with v over v dotted with v. This is again just a scalar multiple times vector v. And this is true for any vector u and any vector v. Let's apply this formula onto the left-hand side, and we'll easily get the right-hand side with the familiar properties of the dot product. So, projection of u onto kv. It is this vector, so u, dotted with the vector we are projecting onto, and here this is kv, over the vector we are projecting onto dotted with itself. So we'll have kv dotted with kv, that's our scalar multiple, times the vector we are projecting onto. times vector kv. Well, simple property of the dot product, we can move scalars onto either vector and also out of the dot product. So if you recall, k times u dot v is the same as k u dot v, and that's the same as u dot kv. So we'll pull this k out, but this is also a scalar multiple, so we'll pull this k up front, this k up front, so we'll get k squared, and we'll be left with u dot v over, same thing here, we can pull both k's outside of the dot product, and we'll have k squared, and we'll be left with v dot v. Times, we've pulled this k out, and we're left with times v. Well, if k is not 0, k squared over k squared is 1, that's gone, and we're left with, would you look at that, u dot v over v dot v times v. So that's just a projection of u onto v. And this completes the proof. So if you project u onto v, or project u onto any other vector parallel to v, the projection is the same. In our next video, we will consider a property of a line in the xy plane and find a very special vector that is perpendicular to it, and then we'll use a projection to solve a distance problem.